Late on May 26, 2026, forecasters at NOAA's Space Weather Prediction Center confirmed that a negative polarity coronal hole high-speed stream had begun making contact with Earth's magnetosphere, arriving precisely as modeled, carrying solar wind accelerating toward 500 kilometers per second, unsettling geomagnetic conditions toward KP index 324 by the close of this day, with isolated G1 storm intervals forecast to develop through May 27th and 28 as the stream fully engulfs the planet's magnetic envelope. And active region are for 446, already the largest sunspot cluster on the Earth-facing solar disk, watches from the surface of the Sun with 9 other numbered active regions primed and ready behind it. If you rely on this channel for science that is grounded in verified data and explained with honesty, subscribing ensures that none of this reaches you late. This work depends on the audience that values it. Every figure in this script was drawn from official scientific and governmental sources: NOAA's Space Weather Prediction Center, NASA's Solar Dynamics Observatory, EarthSky's verified solar monitoring reports, the Smithsonian Global Volcanism Program, and peer-reviewed research published in journals including geophysical research. Letters in space weather, but official sources are not infallible, and neither is the human process of reading them. Before any decision is made, whether personal, professional, or otherwise, verify independently through the official channels. The sources are listed, the data is public, the responsibility to check belongs to all of us, but that is not even the complete picture. What is arriving at Earth's magnetic doorstep late on this day? May 26, 2026 is not simply a stream of fast-moving plasma from a hole in the Sun's atmosphere. It is the latest pulse in a long, documented, and deeply alarming pattern of solar behavior that sits at the precise peak of solar cycle 25, a cycle that has already exceeded early forecasts for activity intensity, a cycle whose maximum phase was projected to run from late 2024 through early 2026, and which, according to analysts at NOAA and beyond, may still be producing its most consequential events in the weeks and months remaining in that window. What is arriving today is not unusual in isolation. What makes it significant, what makes it genuinely alarming when you look at the full body of data, is the context in which it arrives. Earth's infrastructure is more dependent on electromagnetic stability than at any previous point in human history. The number of satellites in low Earth orbit has increased by orders of magnitude. In the last decade alone, GPS signals underpin financial systems, aviation, precision agriculture, maritime navigation. Power grids in high-latitude nations stretch for thousands of kilometers across terrain that functions, in effect, as a giant antenna for geomagnetically induced currents. The stream arriving now is a G1, a minor storm by the 5-level NOAA scale, and here is where this account becomes genuinely significant. It is not the G1 storm that should concern you. It is what a G1 storm, arriving at the current moment in solar cycle 25, with R4446 watching from the solar disk and 9 other active regions numbered and cataloged, tells us about the system that is producing it and the larger event that system is still entirely capable of generating. Understand what a coronal hole is, and you begin to understand why this stream arriving on May 26th is not a random event. A coronal hole is a region of the Sun's outer atmosphere where the magnetic field lines do not loop back to the solar surface. They open outward, extending into interplanetary space, and through that opening, the solar wind does not trickle. It pours. These are cool, dark regions in extreme ultraviolet and soft X-ray imaging. Dark because they are less dense than the surrounding plasma. Dark because the magnetic architecture that normally confines hot solar material has been torn open. NOAA's Space Weather Prediction Center documents them meticulously. They can persist for months. They can rotate with the Sun, returning to the Earth-facing side every 27 days with the regularity of a tide, delivering high-speed streams on a schedule that forecasters can predict with useful accuracy. The stream arriving now is from a negative polarity coronal hole. Negative polarity meaning that the magnetic field lines it carries point southward. And southward pointing Bs is what matters most when that stream meets Earth's magnetosphere. When the interplanetary magnetic field's B's component turns south and sustains that orientation, it can couple with Earth's northward pointing field, essentially unlocking the door. That coupling is what drives geomagnetically induced currents. That coupling is what heats the upper atmosphere, expanding it outward so that satellite orbits decay faster than predicted. That coupling is what NOAA watches with instruments that run continuously every second of every day, because the difference between an hour of sustained southward Bs and a few minutes of it is the difference between a manageable G1 event and something far worse. The solar wind speed, now approaching 500 kilometers per second, deserves to be stated in human terms. 500 kilometers per second, that is not kilometers per hour, it is per second. In the time it takes a healthy human heart to beat once, a parcel of solar plasma traveling at this speed covers 500 kilometers. For reference, the distance from London to Edinburgh, the full length of Great Britain from south to north, is approximately 640 kilometers. The solar wind covers that distance in a beat. And a quarter of the human heart, it left the surface of the Sun and crossed 150 million kilometers of interplanetary space to arrive here at Earth at this velocity. The stream detected arriving late on May 26th represents plasma and magnetic field structures that departed the Sun roughly 4 days ago, invisible in transit, undetectable to any ground-based instrument until the moment they crossed the L1 Lagrange point approximately 1.5 million kilometers sunward of Earth. where NASA's monitoring instruments provide approximately 15 to 60 minutes of advance warning before impact on the magnetosphere. 15 to 60 minutes, that is not hours, that is not days. That is the full span of operational warning available to grid operators, satellite controllers, and aviation authorities when a fast solar wind stream arrives. Minutes are not hours, and in this context, that difference is everything. The system is not inactive, it is accumulating. R4446, documented in real-time NASA Solar Dynamics Observatory imagery and confirmed in reports current as of May 24 and 25, 2026, is already described as easily the largest sunspot cluster on the Earth-facing solar disk, a fact noted by independent astrophotographers whose filtered solar images have been verified and published. R4447, the lead flare producer over the preceding 24-hour window, fired 4 of 6 C-class flares recorded in that period, including the period's strongest event, a C3, 7-class flare. C-class flares are common. They are the lower end of the solar flare classification scale. They are not the events that disable infrastructure, but they are the events that tell attentive forecasters that a region is active, that the magnetic field lines in that sunspot group are stressed, that reconnection events are occurring. And the question the data poses is not whether R4446 and the other active regions currently facing Earth are capable of producing M-class or X-class events. NOAA's own forecast, current as of May 25, 2026, places a 35% probability on isolated M-class flares. The question is not whether, the question is when, and whether the B's component of whatever comes will turn south at the moment of arrival. Here is where the historical record presses in, and it presses with a weight that makes the current moment impossible to consider lightly. On March 13, 1989, a geomagnetic storm classified at the highest level of the space age KP index 9, a number that corresponds to the top of the scale, a disturbance described by Dr. David Bottler, head of the Space Weather Group at Natural Resources Canada, as the biggest geomagnetic storm of the space age arrived at Earth following a coronal mass ejection associated with an X4, 5-class solar flare on March 10th and an M7, 3-class flare on March 12th, 2 CMEs, the first cleared a path through the ambient solar wind. The second struck with force amplified by the cleared channel, a phenomenon that researchers studying the Carrington event of 1859 and the Great Railroad Storm of May 1921 recognize as a recurring pattern in the most extreme geomagnetic events in the documented historical record at 2:44 a.m. local time. On March 13th, the Earth's magnetic field over Quebec was fluctuating violently. The protection systems on hydro S735 kilovolt transmission grid were triggered, 5 high-voltage lines from James Bay tripped, a generation loss of 9,450 megawatts followed within seconds. The system was carrying a load of 21,350 megawatts at that moment. It could not sustain the imbalance. The entire grid collapsed in less than 90 seconds. 9 million people across the province of Quebec lost electricity. They lost it not 4 minutes. They lost it for 9 hours at 2:44 in the morning in a Canadian March, without heat, without light, without the infrastructure that modern life assumes is permanent. The financial damage documented in material costs alone reached $13.2 million. This is not a hypothesis. This is documented in the governmental record. It has already happened once. The record of it is still preserved in the operating manuals, the upgraded protection systems, and the real-time alert infrastructure that Hydro was forced to construct in the storm's aftermath precisely because no precautions had been possible at the moment of impact. Quebec sits on the Canadian Shield, a massive ancient formation of Precambrian rock that is electrically resistive, meaning it does not easily allow geomagnetically induced currents to flow through the Earth as they would in soil or sediment. When the induced currents arrive, they find the path of least resistance not through the ground but through the power lines themselves, treating the high-voltage transmission infrastructure as a conductor, flowing into transformers not designed to carry direct current, saturating them, generating heat, causing voltage oscillations that cascade through interconnected systems at speeds no human operator can track or counteract in real time. Long transmission lines in sparsely populated high-latitude regions, the kind that characterize not only Quebec but Scandinavia, Finland, Scotland, the northern United States, parts of Russia are especially vulnerable. They function during a severe geomagnetic storm as antennas, gathering induced current across their entire length and concentrating it at substations and transformers. Think about that in concrete terms. The person in a high-rise apartment in Montreal who reaches for the light switch at 2:44 in the morning, the nurse on duty at a hospital in Troyes, whose monitors blink off the man in a small home outside of Chicoutimi who woke to darkness and cold and had no understanding in those first seconds of what had just happened to the sky above him, to the sun 150 million kilometers away that had just sent a pulse of energy across interplanetary space and rerouted it through the wires running past his front door. 9 million people. That was 1989. The current population of Quebec is approximately 1 million. In 37 years, it has not grown appreciably beyond the number of people who sat in darkness that morning. If the storm that arrived then arrived now, with the upgraded grid hardening that Hydro has implemented since 1989, researchers estimate the modern system could handle a 1 in 100 year geomagnetic event. The March 1989 event was assessed as a 1 in 50 year storm. The Carrington event of September 1859, the largest geomagnetic storm in recorded history, was assessed as at least twice as intense as any storm in the preceding 500 years, arriving at Earth in only 17. 5 hours of transit time made possible, researchers believe, by a prior CME that had cleared the ambient solar wind and producing auroral displays visible as far south as the Caribbean and Central America, disrupting compass navigation at sea, starting fires in telegraph relay stations, and driving magnetometer readings completely off-scale at observatories in London. The British Geological Survey's digitized records of that event, published in the peer-reviewed journal Space Weather in 2024, document magnetic field variations of measured amplitude data preserved on photographic paper at the Kew and Greenwich observatories, data that had never been fully digitized until researchers studied it again 165 years later to understand exactly how extreme an event the planet had already survived before a single power line existed to be disrupted by it. Scientists choose their language carefully here, and that careful language is itself the warning. When researchers at NOAA write that a G1 storm carries the potential for weak power grid fluctuations, minor impacts on satellite operations, and auroras potentially visible at high latitudes such as Canada and Alaska, they are not describing a catastrophe. They are describing a lower boundary. They are describing the beginning of a scale that extends upward through G2, G3, G4, and G5, and what the official documentation of those higher levels includes is not weak fluctuations, but voltage corrections in high-latitude power systems, widespread voltage control problems, possible grid collapse in areas like the Pacific Northwest and Scandinavia at G4, and at G5 the level the March 1989 storm reached complete grid collapse in high-latitude regions and extensive grid damage. The G1 arriving tonight is not G5, but it is the same system. It is produced by the same sun, it arrives through the same interplanetary space and interacts with the same magnetosphere that absorbed the G5 of 1989. The distinction is not architectural. It is a matter of solar wind speed, magnetic field orientation, and the behavior of the B's component at the precise moment of arrival factors that no current model can predict with certainty beyond the 15 to 60 minutes of advance warning provided by upstream monitoring. The connection to broader systems is not speculative. A study published in Geophysical Research Letters in May 2026, analyzing 67 years of recorded data, found that a single strong geomagnetic storm can produce dramatic and measurable changes to local weather patterns, effects that current climate models have largely ignored because solar brightness varies so little across the solar cycle that direct radiative forcing appears minor. But the new findings point to a different mechanism. Fast magnetic storms in the upper atmosphere produce a signal that propagates downward into the lower atmosphere, affecting weather on timescales far shorter and with effects far larger than the slow 11-year solar cycle would suggest. The researchers described the finding as startling, a recognition that geomagnetic storms interact with Earth's climate system through pathways that the scientific community is still actively mapping. At the same time, in low Earth orbit, the atmospheric expansion driven by geomagnetic heating causes drag forces on satellites too, increase faster than orbital mechanics models predict. A 2025 study analyzing tracking data for 523 Starlink satellites across the rising phase of solar cycle 25 found that satellites re-enter faster under elevated geomagnetic activity, and that prediction errors increase during those same periods, meaning that during the moments when precise orbital knowledge matters most, the data becomes least reliable. The world currently operates more than 8,000 active satellites in low Earth orbit. Each of them is affected when the thermosphere expands. None of them carries an option to simply pause until the storm passes. Consider the city of Troms, Norway, situated at approximately 69.6 degrees north latitude, well above the Arctic Circle, deep within the Aurora Lovel, a city of roughly 77,000 people, where the northern lights are not rare events but regular features of the winter sky. Troms hosts research institutions, hospital infrastructure, and maritime navigation systems for some of the most economically vital shipping lanes in the North Atlantic and Arctic. When a G1 storm arrives, the KP index remains manageable and the city continues to function. When a G3 arrives, a strong storm, KP7, the kind of event that NOAA's May 2026 forecast window already identified as possible during the May 15th to 17 storm period, Troms's power infrastructure operates under stress, induced currents flow through the Norwegian grid operator, Statnett, monitors geomagnetic activity continuously, but monitoring is not the same as immunity. A person in Troms waking in the night to a power interruption caused by geomagnetically induced current saturation of a transformer does not experience a number on the KP scale. They experience darkness, loss of heat in an Arctic environment, and the particular modern helplessness that comes from having no backup for infrastructure. They have never been asked to imagine losing. That helplessness is not Norwegian in character. It belongs to every high-latitude city whose grid runs long lines across resistive geological substrate. It belongs to Helsinki and Reykjavik and Anchorage and Edmonton. It belongs to the infrastructure layer beneath modern life that nearly everyone uses and almost no one thinks about until it is gone. The Sun is currently in the peak activity phase of solar cycle 25, a cycle that began in December 2019 and whose maximum, according to NOAA's Space Weather Prediction Center, was projected to occur between late 2024 and early 2026, with some analysts noting in November 2025 that the maximum Phase may extend further. Solar cycle 25 has already exceeded early predictions for intensity, producing multiple X-class flares, several CME events, significant geomagnetic storms including a G1 event confirmed by NOAA at KP5 on April 30, 2026, and a G2 storm confirmed in mid-May 2026. R4446, the largest active region currently on the Earth-facing disk, announced its arrival on the solar east limb with, in the precise language of EarthSky's solar reporting, a bang. The region is being watched. R4441, R4447, and 7 additional numbered active regions accompany it on the current Earth-facing solar disk, 9 numbered active regions. In a quiet sun, that number might be 1 or 2. 9 is not a quiet sun. 9 is a sun at the height of its cycle, organizing magnetic field configurations of enormous complexity across its surface, storing energy in stressed field lines that reconnect and release as flares and CMEs on timescales that no human instrument can fully predict. What the official data actually shows is this: the stream arriving late on May 26, 2026, is the leading edge. The leading edge of a coronal hole high-speed stream that will peak on May 27th and 28, with solar wind speeds potentially reaching 500 km per second, with NOAA forecasting KP3-24 unsettled conditions transitioning to isolated G1 storm intervals if the B's component of the arriving stream sustains a southward orientation during those peak hours. The geomagnetic response will intensify. If R4446, which has already demonstrated its capacity to produce flares in the days since its east limb arrival, produces an M-class or X-class event in the coming hours and days, and if that event is associated with a CME directed toward Earth, the stream already arriving from the coronal hole provides a ready-made highway, a partially cleared channel through the ambient solar wind that any CME would traverse faster and with less deceleration. This is not speculation. This is the documented mechanism that made the March 1989 storm the most powerful of the space age. 2 CMEs, one clearing a path, the second arriving with amplified force through the cleared channel. Scientists choose their language carefully here. The forecasts for the current period note a 35% probability of isolated M-class flares. They note a coronal hole high-speed stream arriving on schedule. They note unsettled to active conditions. They do not use the word alarming, but the data, read in full, in context, against the historical record, by someone who has sat with the numbers long enough to understand what they mean, produces a different register entirely. The infrastructure most at risk is not the infrastructure most people think of first. It is not the phone in the pocket, though satellite-dependent navigation underpinning that phone's location services is genuinely affected during moderate to strong geomagnetic activity. It is the transformers. Large high-voltage transformers, the kind that sit in substations and step current up and down across long-distance transmission lines, are custom-built, not mass-produced. Replacement lead times run from months to years. The transformer that absorbed induced current during the March 1989 storm at the Radisson substation on Hydro. S-system, the one where 220 amperes of geomagnetically induced current were measured flowing through a single unit, was damaged. Its replacement required months of procurement. During the 9 hours of the 1989 blackout, the people of Quebec experienced discomfort. During a scenario where the transformers themselves are damaged rather than simply stressed, a scenario documented not as speculation but as the assessed consequence of a Carrington-level or even Great Railroad storm-level event, the recovery timeline is not 9 hours. It is months, months without large-scale power. Months for a population that has built every layer of its daily existence: food storage, water treatment, hospital operation, communications, heating, financial systems on the assumption of continuous electrical service. And here the data offers no comfort because the data shows that events capable of producing that outcome have already occurred. The Carrington event reached Earth in 5 hours. The 2012 solar storm, a CME whose energy and magnetic field configuration were comparable to the Carrington event, missed Earth by 9 days. 9 days, not 9 years, not 9 decades, 9 days. Had that storm CME been aimed 9 days earlier, it would have struck a civilization that had replaced telegraph wires with fiber optic cables and power grids and satellite constellations and global positioning systems and financial networks that clear trillions of dollars in transactions daily using electromagnetic signals. Ice-core samples analyzed from sites in Greenland and Antarctica preserve evidence of extreme solar proton events extending back 9,000 years, with one event approximately 774 years ago, now known as the Miyake event, estimated to have deposited radiocarbon in the atmosphere at a rate 60 times higher than the Carrington event. The geological record does not care about the human timeline. It simply holds the evidence that what has happened before will happen again, and that the sun operates on its own schedule, indifferent to the infrastructure built by the species living on the third planet of this solar system. What the current moment requires is not panic. Panic is not a scientific response, and it is not a productive one. What it requires is a clear-eyed understanding of what the instruments are showing. Late on May 26, 2026, a negative polarity coronal hole high-speed stream is arriving at Earth's magnetosphere. Solar wind speeds are ascending toward 500 km per second. 9 numbered active regions sit on the Earth-facing solar disk. R4446, the largest, is still rotating into full Earth-facing geometry. NOAA's Space Weather Prediction Center has issued forecasts for unsettled to active geomagnetic conditions through May 27th and 28th, with isolated G1 storm intervals possible. The monitoring infrastructure is in place, the detection systems are functioning, grid operators in high-latitude nations have real-time alert systems. That did not exist before 1989. Airlines can reroute polar flights when solar radiation advisories spike. Satellite operators can adjust operational parameters during elevated geomagnetic activity. The tools exist that did not exist when the lights went out in Quebec at 2:44 in the morning. The question the data leaves open, the question that no monitoring system, no forecast model, and no operational protocol can answer in advance, is whether the Sun, at the peak of solar cycle 25, with 9 active regions on its Earth-facing disk and a coronal hole pouring high-speed plasma into interplanetary space right now, will produce in the coming hours and days an event that tests those tools to their limit or beyond it. The system is not inactive, it is accumulating, and the Sun has been doing this for 6 billion years, storing energy in magnetic fields, releasing it in ways that no instrument built by a civilization that has existed for a fraction of a single solar cycle can fully anticipate, long before the first telegraph wire was strung between 2 cities, long before the first high-voltage transformer was installed in a substation on the Canadian Shield, long before the first satellite was placed in orbit above an atmosphere that expands when the solar wind arrives and contracts when it passes, as it has always done, as it is doing right now, at 500 kilometers per second, against a magnetic shield that is the only thing standing between the surface of this planet and the full force of what the Sun is sending.